Matt, can you hear us? Matt, can you hear us out there? Maybe not. Ugh. Hello, Matt. Can you hear us? Well, we are recording this meeting, so if anybody misses what we're saying, I can always share the recording with them. All right. I think I got some messages here. Lane, Matt, can you hear us?
Yep, I can hear you.
Excellent.
Finally got that equation to work.
Oh,
It
bad.
took me like all last night.
That's always fun, isn't it?
Yeah, I kept getting different answers every time I tried it. So
Ugh, that's the problem when you get into a class like this is you tend to have complex mathematics that can be a little bit difficult to make them work out just right. Tiniest little error causes a big problem at the end of the math.
yeah,
The way we used to do so, one of the things that I try to recommend to students every semester, but it's getting harder and harder to recommend it, is to work in study groups. But as I go further and further down my career path, I find that I'm teaching more and more students all over the place. And it's more and more difficult for them to get together and work in groups. And the reason that it's useful to work in groups is that we would all do the same problem and do it maybe slightly different ways, but then we would just come together and say, so how did you do it? What did you get in the end? And we'd compare the results like step by step, and then we'd be able to find our mistakes better that way. And that's kind of the way that I grew up doing physics and math, was by working in groups and comparing so that you could find your mistakes. Back then, of course, we didn't know if our homework was right until we got it back. And usually by the time we got it back, we were 2 homework assignments down the road and we didn't have time to look at it or check it. There was like usually that one student who was like the brilliant one who spent half as much time on his homework as everybody else. And they had time to check their homework, but the rest of us didn't. So we had to check it before we turned it in order to learn anything. So anyway, the advantage that you have is you know that it's wrong right away, and you can look for the problem right away, even if it does require you to do the problem several times. Unfortunately, that's the downside. But at least you can learn about it right away instead of waiting or whatever else. But I still recommend that. I still recommend that if you're looking for a different way to study or a better way to study, to try and study with somebody. If there's somebody in your area that's in the class, or if you want to jump onto Zoom and study with somebody, I'm more than happy to set up a Zoom meeting for you. I mean, of course, you can set up your own Zoom meeting, but if you don't have a professional account, then you can't set them up for like forever. Like if I start a Zoom class and I forget to turn it off, it goes forever. And I actually recorded a class for like 72 hours.
I think I definitely saw a video like that on YouTube.
Yeah, one of my YouTube videos is like 72 hours long of just like blank screen and nobody talking, random lights turning off and on as people going out of there. It was pretty funny. At some point, I should probably go in and edit that video, but I think it's just kind of funny the way it is.
yeah, I was gonna say leaving it as it is. It's
People
kind
like-
of funny.
People like scrolling through the video looking for a problem. They're just like, it's just another blank screen. Sorry, what did you say?
I just said, yeah, leaving it like that would be pretty funny.
Yeah, maybe it'll go viral. I actually got a comment on one of my, because I've posted hundreds and hundreds of videos of my classes, and and I teach this programming class next semester, but I'm not a I'm not a very good programmer. I hate programming. And it's just never been something that I've really excelled at, even though I've been doing it all of my life. I mean, I've been programming since 1980, and that's a long time. That's 40 years, and I'm just about to turn 50. So since before I was 10, I've been programming, and I grew up with computers. My dad worked for NASA when I was a kid, and he was working on computers long before that. Even he worked on computers. So when I was a kid, he would give us a list of jobs every Saturday we had to do before we could play. And he gave us this list of jobs on punch cards that were used to program computers back in the 60s and the 50s. This is what they looked like. So this is what I got my jobs on every morning, were these punch cards. What? I don't want to purchase them. I want to just look at them. Goodness gracious. Images. Here we go. So this is how you used to write a program in my dad's day. These things are about 3 inches wide and about 8 inches long-ish. And you literally had like a typewriter machine that you would insert one of these things into, and then you would push buttons on this typewriter thing, and it would punch holes in this card. And one card was essentially one line of code, and that's it. So you were literally just putting in machine code into these cards, and then you would have a stack of these that you maybe have a program that would take up 50 boxes of these cards, and then you'd put these stacks of cards in a machine, a card reader that would run them through automatically, like those money counting machines. It'll run these cards through, and it would read the program on the card, and then eventually it would take maybe it could take 10 minutes or maybe even 2 hours to run all these cards through and load that program up onto the 12 kilobytes of memory that are on the computer or whatever it is. It would load, and it would run that program on the computer, and then all the data that would come from that program would be put onto tapes. It would be recorded onto tape drives in the next room. And then when you turned off the computer, that program was purged from the computer, and you'd have to load it again the next time you wanted to do it. And my programming experience is not quite that old, but that's the guy that taught me to program. That's where his experience came from. And so I've been doing it all my life. I hate it. I'm not good at it. And I make these videos all the time for my students because they want to know what went on in class and what we learned in class. Well, I didn't know that anybody online would ever watch one of my videos, but somebody did. Like, I made a video that was called Graphing in MATLAB or something like this. And so they watched it, and they're like, "Are you a professional? Because you're not very good at this." Like, I'm not a professional, and you're right, I'm not very good at this. I think they were trying to be insulting or something, and I'm like, no, I'm never going to admit that even if I was good at programming, I probably wouldn't admit it, because it's not a really good social thing to be good at, right? If you say you're good at programming, everybody thinks, well, he's obviously probably not very good at social interaction. It's not always true, but it is very often true. I don't think I could honestly say that I can say that I've never really met anybody who was an insanely good programmer who is socially like there. I've never met anybody like that. I've met people that are pretty good at programming and are socially, whatever, cool, whatever, but I've never met somebody who's insanely good at it. Most of the people that are insanely good at it that I've met have really like embedded genetic social issues. It's not even just, they're just not comfortable around people. It's actually like Tourette's or something. I've actually met somebody who has Tourette's who's an incredible programmer, but when they're in any situation, really, they just can't be social. It's incredible. But he is an incredible, and he was also a great physics. He was in my physics. He was one of my students when I was teaching physics as a graduate student. But anyway, great guy. But socially struggled a bit. He's also a millionaire now. Like, there's advantages sometimes to being a great programmer, even if it comes with a little bit of a social problem. But anyway. So that's just kind of a funny aside there just for the sake of goofiness. All right, so I see that I have some messages here. I hadn't seen those before, but I will check after the class and make sure they get those answered. Those questions answered. I did have several people that asked questions. Did we have the cat on the board question in this class? Or is that?
We haven't said chapter yet.
What's that?
We haven't said chapter yet. I don't know about capital board, but probably not, I guess.
Okay. Are we done with chapter 7? We're not quite done with chapter 7.
Chapter 7.
I don't think we did the last section, did we?
I don't remember us talking about power.
Yeah, I don't think we did the last section. And that's why I put the homework till today. So let's talk about power really quick. We've talked about energy. We've talked about kinetic energy. We've talked about work. We talked about energy, the work required to move something in a gravitational field, which introduced us to potential energy. Turns out that this book has a chapter on potential energy. So for chapter 8, and so we'll get to that again. Yeah, we definitely haven't talked about the cat on board, so that's the other class. Okay, so anyway, but now we're going to talk about power really quick. And power is the last thing in this chapter. So power it's really quite a simple concept, actually. Power, although it's very often misunderstood and misrepresented, power is the amount of energy that you're using per time, over time, right? So if let's say, for example, if I'm running a marathon, let's say, and in the marathon, let's say that I'm using 5,000. Well, this is probably outrageous. Let's say that I'm using up maybe 500 joules every second. Okay, so 500 joules every second. Well, 500 joules is a measurement of energy. If I'm using it every second, that's energy per time, energy every second. It's kind of like velocity for energy, right? But the problem is that people say, how much power did you use? That's a bad question. How much power did you use? You don't ask somebody, how much velocity did you have? You know, you say, what is your velocity? That's how fast you're moving, right? It's not, it'd be the equivalent of asking, how much velocity did you use? Or how much velocity if you're running the marathon, you say, well, how much was your velocity, for the whole marathon? Well, there is no velocity for the whole marathon. You speed up, you slow down. It's a rate of change. There's a distance of the marathon. There's a total distance of the marathon, but there's not a velocity of the whole marathon. You can have an average velocity over the entire marathon, but you're always speeding up, slowing down. But energy is something that you measure in quantities. You have so much energy that you use during a marathon. But if you used 500 joules per second, that's how fast you were using it at that particular moment or through the course of, a few seconds or whatever. So power is how much energy you're using per second. Now, in terms that we actually use this regularly, we have usually electricity is where we talk about power, but energy use can be in any realm. It doesn't have to be in electricity. But in the electricity realm, we talk about this quite a bit. And so this is where it's most often misunderstood. We say, well, this power plant is a 1 megawatt power plant, for example. 1 megawatt is 1 million watts, and a watt is 1 joule per second. So that 1 megawatt would be equivalent to 1 million joules per second. Okay. And that doesn't mean that's the amount of energy that power plant has. That's how much energy it puts out every second. So every second that thing's running at full capacity, it's putting out 1 million joules of energy, right? The other time when this is grossly misunderstood tends to be with machines or systems that use energy. So we say something like a 60-watt light bulb, for example. You have a 60-watt light bulb and it's using 60 joules per second of energy, right? Well, that seems fairly simple. But what if you have a 5 gigawatt laser, right? Light bulbs are, we turn them on and we leave them on for quite a while, right? So it makes sense to say 60 watts. That makes, that puts in your mind a light bulb that's staying on for a while, and a 60-watt light bulb can light up a normal sized room. And so we can think of that energy being turned into light, and it turns into some heat as well. But a laser is usually only turned on, especially a very high powered laser, is only turned on for a fraction of a second. So if you have a 1 gigawatt laser, right, or a 5 gigawatt laser, and it's only turned on for 0.001 seconds, 1 millisecond, then all of that energy in that tiny little time has to equal the 1 gigawatt. So this is what it looks like if we do the math. 1 megawatt, and people think 1,000,000 watts, that's tons. I mean, 1 megawatt is how much a power plant puts out every second. And if you have a 1 gigawatt laser, then that's 1,000 times more energy that you're using in that laser. And people look at scientists and they say, you're wasting energy if you're using a 1 gigawatt laser, because that's more energy than the entire power plant puts out. But it's not energy, it's power. Power is energy per time, and this gigawatt laser is only on for 0.001 seconds, okay? Or even shorter than that, okay? So if you say the power is equal to the energy, and here they write it as the work, the energy over the time, and the time is 0.001 seconds, right? And the power is equal to 10 to the 9, which is which 10 to the 9 is gigawatts, right? Then you multiply by 1,000 on both sides to get rid of the 0.001, and all of a sudden you're 1,000 times. Sorry, you don't multiply by 1,000. You multiply by 0.001. Sorry, 0.001 to get rid of the 0.001 on the bottom, not by 1,000. Then you multiply by 0.001 over here, and all of a sudden you're 1,000 times smaller over here. So it's only 1 megawatt of energy. Sorry, only 1 megawatt. It's only 1 megawatt of. Sorry, I'm doing this all backwards for you. I need to restart this because I actually characterized lasers incorrectly without thinking about it. Usually when they talk about lasers, they talk about joules. So they say it's a 100, so it's a 1 billion joule laser. So it's 1 gigajoule. So all these zeros up here, there's your energy. And then the time goes down here. 0.001. Sorry, this would be megajoules. And then that becomes the 1 billion, 10 to the 9 right there. Right. Because if you divide a million times 0.001, you get a billion. It's the same idea though. The idea is that these numbers we don't think in these terms very often. We don't think in terms of small time scales. And so a laser that has, it's a laser that's actually a 10 or a 10 to the 9 watt laser or a 1 gigawatt laser is only using 1 million joules of energy. And so, and that's still a lot of energy, but it's not an insane amount of energy. You can get that amount of energy out of a power plant in 1 second. So it's not like these scientists are wasting energy in the world. They're not. That's 1 second worth of energy out of a power plant that's open all the time. Right? Anyway, the point is that this is misunderstood a lot. The idea of power is misunderstood quite a lot in the world. But it's not that difficult. It's just energy per time. It's how much energy you're using over a certain amount of time. And you have to actually divide by that time to get the energy. So plain and simple. Of course, if we have energy involved and it's work being done, which it often is, then work we know involves the dot product, first of all, between the, the force applied and the displacement and so on and so forth. And it also, if that force is changing over time and the path is changing and everything else, you have to do an integral over the differential work. And so we know that we've been doing that all along. So it looks more like this. The power is the derivative of the work with respect to time. And if you're going to calculate the work, you're going to have to actually do a time derivative anyway, and so on. So that's just stuff we know mathematically, and we can deal with it if we have to. But let's just look at it in a very simple way. We have an 80-kilogram Army guy. He's doing pull-ups on a training bar here. It takes him 0.8 seconds to raise his body from the low position to the high position, and the change in height is known. And we're going to calculate the work done. The change in height is going to be 2 feet 60 centimeters. The amount of force that he has to apply is going to be the weight of his body, equal to the weight of his body. So M times G. So it ends up being M times G times delta Y is the work being done. And then the time is 0.8 seconds. And that turns out to be 500 watts right there, doing one pull-up. If you do one pull-up in 0.8 seconds, it takes 500 watts, 500 joules per second. It's 529 joules per second to do that, to do pull-ups. And that's actually a pretty high amount of power for a human. If you try to do pull-ups, your average human can only do a few pull-ups before they're done. Like they're so tired, they can't lift themselves anymore, like not even an inch. And we're talking, I think the average for human beings is like 0.7 pull-ups. Most people can't even do one, right? It's true. It's true. Most people can't do even one pull-up. They're not easy exercises to do. Of course, this is averaging across the entire spectrum of the human race, age and everything else. So that's not too surprising. But that gives us an idea for how much 500 watts is. If your body is putting out 500 joules every second during an exercise, it's a lot. It's more energy than your body can provide for most people, right? And for people that run a long distances, they're also putting out energy at that level. It's actually a very difficult thing to do, to run long distance, or most people can hardly run a quarter of a mile. Probably even less than that, 100 yards is probably the average for human beings. Run 100 yards and you're just too tired to keep running, you got to stop and walk, or just stop altogether. So 100 yards running for most people is less than 25 seconds. That's how much energy this is. It's 500 watts every second for 25 seconds is about what your average human does before they just have to stop and not do anything for a while, right? So it's a lot of energy. If you do 529 watts of power, if you output that amount of power for 10 seconds, how much energy are you putting out total? Well, let's take a look. Power is equal to energy over time, or work over time. And if we want to know how much time that is, then we solve for the work. Work equals power times time. So if we're doing 529 watts, which is the power, and we do it for 10 seconds, that's 5,290 watts. Or sorry, 5,290 joules, because we just calculated energy. And that's equal to about 1 food calorie. Right there. So 1 food calorie gives you about maybe 100 yards of running. It gives you about 10 pull-ups. 10 pull-ups will do 1 food calorie. How many calories do you eat in a day? Average? A couple thousand?
There's do we eat, or our calorie calculated by regular calories or the metric?
So this is actually food calories. So food calories are 1,000 metric calories. So a food calorie is different than like calories that are defined by the metric system.
And calories with C.
Yeah, it's either calories with a K or C, or capital C and little c, or whatever else. I don't know. We don't use them in physics very much, but we use joules. But this is, 5,000 of these joules is equal to about 1 food calorie. So it's like 4,000 something. But if we're eating 2,000 calories a day, that's how much energy we're putting into our body. Now most of that energy is not being used to do things other than heat up our body. And some of those calories go straight through our body. Some of them go out as waste. In fact, most of them do. But we're left with at least a couple hundred calories every day that we have to burn off by doing some kind of exercise. Probably in a 2,000 calorie diet, your average person is probably left with 50 to 100 of these calories, somewhere in that range. I don't know exactly what the numbers are, but somewhere in that range of many tens to a few hundreds of calories that we have to burn off. Walking is not going to take 500 calories. It's not going to be 500 watts, not 500 calories per second, because walking is not nearly as strenuous as doing pull-ups or running, right? So walking will give you a far lower rate of calorie burnage or far lower rate of power usage than running. So if you want to do pull-ups to get rid of 50 calories, you have to do, 10 pull-ups gives you 1 calorie. You have to do 50 pull-ups, right? That's, or 500 pull-ups rather. That's a lot of pull-ups to get rid of all those calories. So this is this is very much tied into the thermodynamics of the body, of the human body, and it's tied into the energy use in everything. The energy that gets passed around in the universe for everything. So anyway. Power. Here's what happens mathematically when you do this differentially. You have the work, the differential work is equal to the dot product between the force and the displacement, right? And then you can actually just make that displacement a drdt. You essentially move that time derivative to the displacement, and that drdt is actually a velocity. So we actually find out that the power is actually equal to the dot product between the force and the velocity. Well, that's actually kind of useful because it's much better than doing a bunch of derivatives and stuff. Here we have a car moving along. We want to know how much power the car is using as it's going up this hill. How much power, how much energy per second, right? 1,200 kilogram car, 15% grade, 90 kilometers an hour. So they've given us the velocity, right? And they tell us, they've told us previously that the force times the velocity, that F dot velocity, force dot product with the velocity, is going to be getting us up that hill. So what is the force required to go up that hill? Well, the force is going to be the weight of the car is the force that you have to exert, excuse me, to get it up the hill. But the velocity and the weight are at different angles, right? So the velocity is this way, but we're lifting the car this way. Now you say, well, wait a second. Sorry, the velocity is not that way. The velocity is this way. There we go. And we're trying to lift the car this way. So that's essentially what we're lifting against the weight. And you say, well, wait a second, that's not the way we're lifting it. We're lifting it this way. But the velocity is the thing that tells you the direction you're going, not the force. So the force is just what kind of force do you have to do? And the force that we have to do is the force that we have to put into this is lifting it. Now they did tell us that 25% of this energy is going to be used, or 25% of the power is going to be used along the path to overcome resistance. So we can take care of that later. But this end up being the two vectors that we are going to apply to it. We have the force and we have the velocity, and this angle between them is going to be this 15% thing that we're going to put in there. Now, do they draw a picture of this? I don't know if they do or not. Let's see if they do. They don't. That's okay. But they give us that angle, and we know that the dot product is going to result in the sine of that angle. And so we can go ahead and calculate that. And then once we've calculated that, we only take 75% of it because 25% of it is lost to friction. And then we can calculate it here. Fairly straightforward.
If there was a problem like that, and the friction is given, so just saying 75%, it's at 70%, 5% effectiveness, where would the friction go in that equation?
Where would the, what do you mean, where would the friction go?
Like, so you were given a friction value, maybe 600 newtons.
Oh, I see what you're saying. Okay, so let's draw this picture differently. And I can see what you're asking, but to answer that question, we need to do the entire problem. I was just kind of skipping through the problem, just trying to let you fill in the blanks. But if we're going to answer that particular question, which is an extension question, we do need to draw the picture out and do it completely. And that's a good question because it's going to illustrate something that I hope is useful to you. So I'm going to draw my slope here, and I'm going to draw it extremely so that we can see the angles. And we're going to do this instead of using the energy version, which is the fast, quick version. We're going to set this up with forces, which is useful because that'll help us to calculate the works as well. If we have our car going up this slope, here's our car. Now, whenever we've done problems like this, we know that mass goes straight down like this, mass times gravity, the weight of the car, right? And now what we're going to do is we're going to develop all the components of these forces. We're going to rotate our axes. So our axis is like this now. We'll call this X and call this Y. And this is going to be our Y component of our weight, and this one's going to be our X component of our weight, right? So if this one is M times G, then this one here is actually M times G. This is theta right here because this is theta. That's our grade, right? This is theta. So this is going to be M times G times cosine theta because it's next to there.
I think that's a better question. You gotta,
This answered your question already?
while
This-
we were working through that, I realized something else about, because this is a question on the homework, and I realized how to answer it. There was another question on the homework actually that was stupid and did it a really hard and convoluted way. What instead of just realizing that I could do potential energy is equal to the kinetic energy.
Yeah,
The difference between the two would be friction.
yeah, and so that's kind of the idea that I kind of just ran through really quickly. But I'm going to demonstrate why this is the case, and this will actually justify the math from the previous solution as well. So here we have, this is how much gravity is pulling this car down the hill. This one right here. That's telling us how much gravity is pulling the car this way. We know the car is actually going this way. This is the velocity of the car. And we know that there's friction that's going to push against the wheels this way as the car goes up the hill. So that friction is involved. So what we need to do here, if we're going to figure out what the total overall force is, so we can calculate the total overall work, so we're going to have to add all the forces in the horizontal direction. And all the forces in the horizontal direction are the friction, which is a negative force. It's trying to push the car back down the hill. And then the pushing force, which is we're going to have to push up the hill with, and that's going to have to equal this one plus this one in order for it to overcome. So we're going to have friction. We're going to have the friction force that we're going to have to overcome, and we're going to have to push against the mg force as well. Those two added together have to equal our pushing force. So negative mg sine theta, and that has to equal our pushing force, which we'll call F, big F, the great big F, right? Right, so this becomes our force. Now, we know that this part of it is 25% of F, 0.25 of F. That's 25% of our overall pushing force has to overcome friction. That's what they said, right? So then we go ahead and we just assume now that what's left, this part that's left, is equal to 0.75 of F, of the pushing force. Okay. And that means that that's going to also account for 0.75% of the work done. And it's also going to count for 0.75 of the power done. So that's where this comes in right here. Okay. So that's that part. The other part is that F has this sine of theta in it. And when you do the dot product, you're going to end up with a cosine of theta. And you're going to end up with a sine times, you're going to end up with a sine times a 1 over a cosine over a sine or something like this in the geometry. No, a sine over a cosine times a sine in the geometry. But this sine comes in right here, right? So actually, this tangent right here tells us, they actually tell us how to calculate the angle theta. It's tangent theta equals 0.15. Because grade means something different than just angle. But anyway, that's where the sine comes in, is from this guy. And then the theta comes in from this guy. So anyway, that kind of goes back. We're going back to our Newton's second law days to figure out all these forces and to put them all together. But we can actually just do it from the dot product as well, which is kind of what we ran through verbally without actually drawing the pictures. Does that make sense to everybody, or do we need more clarification? Where's my mouse? Can't see my mouse. There it is. I used to be able to like make the mouse bigger. I don't know if I can still do that. I probably can.
You make it wiggle around, it's huge.
Let's see. It's under accessibility, I think. Where is accessibility?
You can go on your buddy's computer and mirror his mouse. So it goes
Accessibility.
in the wrong
Zoom, voiceover. No, it's not where it is. It's under mouse control, probably. No, it's not that either. I don't know where it is. Anyway, who knows where it is? General controls. Don't know. All right, so that is what power is about. Now, there are other units that are used for power quite a bit in the auto industry, for example. They use horsepower. So horses have the ability to put out about 5, and that's actually calculated right here. If you take 58 kilowatts divided by 78, you'll get about that. So it's about 800 something or 700 something, I think. Oh, it's right here, actually. It's 746 watts of power is what a horse can do when they're pulling a wagon or something like this, right? So they can put out 746 joules of energy every second, kind of on average. Yes. What's that? This is average. So you take the average horse from the little tiny ponies, the little tiny horses that they have on Chincoteague Island that are like the size of small dogs or medium-sized dogs, all the way up to the big old like Budweiser horses that pull the big old wagon, whatever. You take the average, and of course the idea of horsepower came in right about the time cars were being invented, because they were trying to compare cars to horses and trying to get people to say, oh, you can buy this little thing that is worth, it has the same worth as 8 horses. But what do 8 horses cost compared to this one little car, right? So they were trying to make a fiscal comparison, and it was very successful in the end. At first, it was not, because the first cars didn't have that much horsepower, and they were quite expensive. But later on became. Did you know the first cars that were really affordable and that actually had enough horsepower to be worth buying were actually electric cars? Back in the 1800s, did you know that? Some of the first cars were actually electric cars. They're actually really cool.
The first cars are super cool, but also super ghetto.
The old electric cars you're talking about?
I don't know if they're really that. Sure. I just know like some of those early stuff with like pretty much all the internals on the outside, on the back of the carriage. Just like
Let me show you an electric car that's one of my favorites. See if I can find it here. Jay Leno owns one. That he takes out when his wife wants to go on a
It
fancy
took a
date.
while to get up
This
here.
is the car he
We
takes.
started
in.
out around 1959. But we didn't do all that just
This
to
is
get
probably
here.
going to get this video
We
not
did it to
posted
give you a
because
truck that'll take you
this is
anywhere.
content from the
This
TV
is the new
show.
Nissan.
YouTube tends to do that.
Now, I've been using Grammarly for
Oh,
years.
cut
Now, the
away,
great thing
stupid
is Grammarly
commercials.
is free and easy.
I need to
to use.
download
Not
an
only
ad
does it
blocker.
check your grammar, but hi, I'm Dennis Gage. Thanks for tuning in to My Classic Car, home with a certified car nut. Today, I'm in one of my favorite.
So here you go.
Baker Electric.
Where's
The Baker Electric.
That's the great thing about it. It's a bit like driving a phone booth. I have to say, it's the only car I have that's 100% maintenance free. I mean, I painted it and restored it, but the windings are such high quality.
It just doesn't break
You
down.
know, it's a turn of the century. They really wanted
Now
to.
this is really cool when you look on the inside.
So,
This is actually the steering bar. That's how you steer it.
Like a boat, like a
Yeah,
boat.
it's like a rudder. You just push this thing forward and backwards, and that turns. When you push it forward, it turns it left. When you pull it backwards, it turns it right. When you kind of hold it in the center, it kind of keeps it straight. And that's it. And it does look like a phone booth on the inside. But these were actually very popular cars back in the late 1800s, early 1900s. They were very easy to maintain. You didn't have to do anything except charge the batteries. And every once in a while, you had to put some distilled water in the battery. And that's about it. Every few years you have to replace the batteries, but they were made with very high quality copper. The wires and the windings were very thick so that there was no overheating going on. Just very well-made car. And this was the first real automobile that was affordable because internal combustion engines are super high maintenance. They can go a lot faster and they're super high performance as far as speed and acceleration and everything else. So nobody was racing Baker Electrics. But if you wanted a car that you could afford, drive around town, this was great. It took, you'd have 8 of these huge batteries in it, and you'd only get about maybe 10 miles on a charge, maybe 20 at the most. On a really cold day, you could get 20. If it wasn't so cold that the batteries were frozen, you could get 20 miles in a day. On hotter days, you'd get less. But these were very popular and very common in the streets of New York and Chicago, and even in small towns in Europe and America. They were using these because they were affordable. Right? Rich people had gas cars because they could go fast. They could burn around corners 30 miles an hour, 40 miles an hour, even 50 miles an hour in some cases, right? And the appeal of going very fast became kind of the driving factor for automobiles at the time. And then it wasn't very long before the oil companies started to make it big in the auto industry. They started to realize that they were going to make a ton of money, and so they started promoting these cars that ran off gas. But the very first cars were actually electric. If we didn't have this need for speed in the human race, this need for like going fast and competing with each other, and it's kind of a machismo thing, it's very much part of our animalistic desire to do crazy things, and I definitely have that in me. Then we probably would never have the argument over whether we're burning too many fossil fuels or anything else, because we would be driving electric cars and nobody would be thinking about it. The coal-fired power plant's far away. We don't think about what it's doing. We don't even see it here in North Platte. It's too far away to see. So anyway, it's just kind of funny the way. And then he actually takes us out for a drive with this guy on the streets of Los Angeles. It makes no sound, hardly.
And away we go. Welcome back to My Classic Car.
There he is, driving through Los Angeles. And the really funny thing is that you're sitting way at the back of the booth.
plus you can look down on other
You
cars.
can actually put people at the front facing backwards. It's no problem.
You do have that kind of superior feel up there.
And the nice thing is you can look down on Prius owners with their gas polluting 3-cylinder, whatever that is motor.
electricity only, and everything, even the lights are electric.
You can look down on
Electric
Prius.
lights.
okay.
Electric lights were a big deal in 1909. Most cars still had gas lamps, so this was all electric. Like when my wife and I go out to eat, I park and I just leave the lights on.
You would think it would actually be that practical to try and like
Yeah.
modify one of these with like batteries from nowadays.
His actually does run off of this one doesn't run off the old lead acid batteries. I think he's using sealed lead acid batteries instead of open lead acid batteries, so much higher efficiency, much better lifespan. I don't know if he's done lithium yet, but lithium ion batteries, I doubt he does because it's just not worth it. And lithium ion batteries are terrible for the environment. So
I was gonna say, yeah, lithium ion batteries aren't good for the environment either, but
so
like,
they're worse than CO2 for the environment by far. Yeah, so the whole electric car craze today is actually doing more to hurt the earth than anything else, unfortunately. But you know, electric cars are cool, so it makes you feel good about yourself to drive an electric car.
in the short term, it's not causing much harm. But when you have to get rid of the battery, yeah.
Well, it's not even just getting rid of the battery, just mining the materials for the battery is when it's
That's
causes
true
most of the
too.
problem. Like
Yeah.
there's an entire province in China that is completely unlivable because of the lithium mines there. And so the company that mines for lithium and all the other stuff that you need for batteries decided to open a mine in California where most of the batteries are being used, because like 70% of the lithium ion batteries in the world are being used in California by California drivers driving electric cars and all the other things that they use electronics for in California. So they tried to open a lithium mine in California, and California absolutely refuses to let them do it. Why? Because they know it's poison. They know it'll ruin their state. It'll ruin a huge swath of California environmentally with all the poison that gets into the groundwater and into the. I mean, the place in China, if you look at images of the abandoned lithium mines in China, it's just a disgusting wasteland. Just looks like, you know, some giant alien just like defecated all over the place. It's just gross. And nothing lives there, like nothing lives there. Nothing will live there for generations to come. So yeah, that's kind of crazy. But anyway, that's power for you. Does anybody have any questions about homework problems? I do see the 2 questions in the My Open Math thing I will answer, but does anybody have any want to?
2 questions. I don't want to ask 2 questions.
They're from you saying?
Yeah, if you only have 2 questions, like they're both the main ones to answer.
Anybody have any questions they want to ask right now? We're done, I guess.
Yeah, I can't think of anything.
All right, well, we'll come back on Friday and we'll start up chapter, whatever is next chapter. What chapter are we in right now? 7, 8? I don't know, 7, yeah. So we'll start chapter 8 on Friday and we'll see you then.
Have a good day.
Thank you, you too.
Does the other physics class, which is general physics, they use the same book as us?
The algebra based class?
The what?
Which other class you talking about? The one that I teach at 9?
I think it's the other physics class that just does, it's in physics